Welcome to the first of 3 videos about API 579-1 ASME FFS-1, which is the Fitness for Service code. I'm talking about Part 16. Today I'm going to share an overview about the technical basis of Part 16. You should watch this video if you want to understand the engineering and science behind how to use information on changes to FRP in service to transform your decisions about repair and replacement. I'm Jeff Clarkson, the Chief Technology Officer and founder of UT Comp. This topic has come up many times throughout my career. In fact, I've asked this question many times as well. Customers need to know if their existing equipment can continue to operate safely and for its intended purpose. Let's dive in. The agenda for these videos is starting with 3 topics. The first one is this video for Fitness for Service assessment. Then we'll talk about evaluation of the data that you get from inspection. Then we'll talk about inspection. The full technical basis for the part can be found in a Welding Research Council Bulletin number 601. It's called an Assessment of Existing Fiber Reinforced Polymer Equipment for Structural Damage. The 4th edition is what we need to use for this. The earlier editions don't include all of the details that we need. Fitness for service is defined as the capability of a component or equipment that may contain damage or defects to be used for its intended service. It's a structural criterion. You actually have to do engineering calculations to do this. You need engineering data in order to be able to determine fitness for service of equipment. The scope of API 579 is for in-service assessment of pressure equipment, so pressure vessels, even storage tanks, piping. It doesn't change, negate, or question any of the construction codes that were used to make the equipment. It supplements in-service inspection codes. So some examples of those are the National Boiler Inspection Code, the Storage Tank Inspection Code, API 653, and so on. It uses specific structural data from inspections to do the calculations. And although it relies on non-destructive evaluation, it actually does not provide inspection procedures or methods. Those are left for inspection standards, inspection codes, or proper certifying authorities. And generally for API 579, each part deals with a specific flaw type and damage mechanism. Examples for steel would be thinning or thickness loss, cracks, creep, etc. There are also 3 levels of assessment identified. Level 1 is the most conservative. Often an inspector or the plant engineer can do a level 1 assessment and determine whether something is fit for service. Level 2 is more detailed than level 1 and often can find that a decision made for level 1 could be relaxed a little bit. It could be fit for service at level 2 because we've involved and incorporated more details, more information, maybe some more measurements. Level 3 is the most detailed and involves more work than level 2. Like construction codes, API 579 is continuously updated. Technologies are generally adopted in the code as they are available. They're not specifically called out. The code doesn't say you have to use this technology or this specific inspection method. It usually calls for inspection to be done to provide information. If new technologies and advanced technologies are available to provide that data in sufficient detail, then they will be adopted. The current situation is that the damage to polymer in FRP can be detected and quantified in terms of the polymer strength reduction. And this has been available since the 1960s. The technology for non-destructive testing to detect damage and strength change of glass fiber does not yet exist. So we do not have anything that measures glass fiber, but we do have something that measures polymer changes very reliably. For the part, we're defining FRP as a thermosetting resin used below the glass transition temperature. A thermosetting resin is, it should be glass, or it is glass-like. It's one of those, it's the brittle thing that you see in most FRP. So even though elastomers are thermosetting, they're not included. And glass fiber reinforcement. Although carbon fiber is being used more and more often, we're keeping this part limited to glass fiber at this time. We don't have a specific reason to not be able to extend it to carbon fiber today. And FRP is a mixture of polymer and glass. It is not an alloy. It is not a solution. It's a mixture. Two materials, and both materials behave differently. The flaw and damage type. Remember I said each part works to a flaw and damage type. For this part, for part 16, the flaw and damage type is creep rupture of the polymer. This is the source of all cracks, all corrosion barrier damage, strength reduction of the polymer, and all joint adhesive failure. Creep starts as soon as service conditions are applied. So as soon as you put FRP into service, it starts to creep. We start to see changes to the materials and the material's strength as a consequence. This can appear as cracks, softening, powdering, thickness loss. The creep of glass fibers also occurs, and it creates a strength reduction of the reinforcement fibers. But this is not directly included. Over time, and I'm actually showing a chart here, the behavior over time is that if we apply a very, very short but large load to FRP, it will fail or burst after a very short period of time. As the time extends with lower loads, we start to get cracking or fracture at different levels. And this chart actually shows that we will lose containment. For instance, a pipe will leak, a vessel will leak, the polymer will crack at much lower loads than glass will, than the reinforcement will. And in fact, that's the thing that we're working to. The design range shown at the bottom represents essentially the factor of safety that's applied to these materials when they're designed to construction codes. When we start getting the strength of the polymer falling into the design range, we start to have cracks form, and potentially we put the reinforcement at risk because we allow materials to come in contact with the reinforcement. What we measure and what we use is something called the polymer damage status. This is a ratio. It's a ratio of the Young's modulus of elasticity of the damaged polymer to the Young's modulus of elasticity of the undamaged polymer. So it's the ratio of how strong it is compared to how strong it used to be. And it's roughly that, because what happens is, with polymers in particular, and glass doesn't do it this way, but polymers, we actually will see a reduction in the Young's modulus of elasticity, and along with that reduction there, we'll also see a reduction in the actual strain at failure, or the elasticity of the polymer. So both of those combine to show that the polymer strength drops even more quickly than the Young's modulus of the polymer. And this is shown on this chart as the lines start to diverge over time. The basic assumptions are that the glass is fully protected by cured and undamaged polymer. That's what we want. We always want the glass to be protected. And the cracks and the defects in the polymer, this is the damage, lead to glass fiber damage. This is completely consistent with corrosion barrier inspection that's been practiced for many, many years, as soon as the corrosion barrier is damaged, we're not sure what the damage to the polymer in the structural layers has extended to. So we very quickly say, well, the corrosion barrier has to protect everything, so we will call this not fit for service. That is not precisely true. It's when the polymer, even surrounding the structural glass, is no longer protecting it. And that's the thing that we're trying to measure. Not trying to, that's the thing that we're calculating on and do measure. We do this mathematically using what's called the remaining strength factor. And what that is essentially a ratio of how strong is it now with damage compared to how strong was it when it was new. And we use only the polymer when we calculate that. So we're not worried about, we know we can't measure what changes have occurred to the glass fibers. So we only measure what happened to the polymer, and we do that based on the polymer. The corrosion barrier is not included in these calculations. Again, we're staying consistent with construction code practices around the world. And for FRP, the remaining strength factor incorporates what thickness do we measure compared to what thickness occurred when or existed when it was new? What's the polymer strength now compared to the polymer strength when it was new? And then we kind of reverse it in order to get it right. We look at what load was it designed to do and what load is actually being applied. Because if the load applied is larger than the load it was designed for, and that happens, we've seen it many times, then that will make the remaining strength factor lower, which is exactly what we want in order to determine whether it's fit for service. So determining fitness for service from remaining strength factor is fairly straightforward. When the remaining strength factor of the FRP that we're assessing is greater than the remaining strength factor that we allow, then it's considered fit for service. Well, how do we know what's allowed? Well, the allowable remaining strength factor for FRP is different than it is for steel as given in API 579. The reason it's different is because FRP equipment is designed with very different factors of safety than steel equipment is. So we're actually using an allowable remaining strength factor of basically 1 divided by the minimum factor of safety that we use in construction codes, and that's 8 for most intents and purposes. So it's 0.125. We've actually found from practical experience that this number works. And as well, remember, we're looking at creep rupture and cracking. We can't allow any open cracks. So if you can detect the width of a crack at level 1, we can't allow it. There are some other features for level 2 and level 3, but we're not going into that in this presentation. The remaining life is one of the last requirements for fitness for service. And on one hand, we can determine whether something is fit for service. On the other hand, how long do we have before some action has to be taken? That's the second question that every owner asks. So we determine remaining life as the time from now, from this assessment, until the polymer will fail. And it will fail when the remaining strength factor reaches the minimum allowable remaining strength factor value. And that can be some years in the future, at which point we determine what that is. And we can calculate that based on the data that we have from the inspection. Now, there may have been some questions raised while you've been watching this. What about acoustic emission inspection? Well, it's included in the Boiler and Pressure Vessel Code, Section 5 and Section 10. Section 10 is for FRP pressure vessels. It's also included in RTP 1. It's fully accepted by API 579. Remember, it doesn't negate or contradict or try to challenge any construction codes. AE testing will always provide a level 1 fitness for service result. There are some features about it that make it a little more difficult, but here's what they are. It doesn't give information to actually determine remaining strength factor. It only provides a fit for service or not fit for service result. And as a consequence, if it's fit for service, it also cannot provide any information that allows us to determine remaining life. Those are some limitations of acoustic emission testing, but it is still a completely valid way to determine fitness for service of FRP equipment. For more details, we actually have some videos giving an overview of design and damage for FRP, and they're available on our YouTube channel. And by all means, check those out. Part 16 determines mechanical integrity of pressure equipment made from FRP. The remaining strength factor is based on polymer degradation before glass reinforcement damage actually occurs, damage from the contents occurs. If you want to know more, I recommend checking out the Welding Research Council Bulletin 601. Now, before I go, I want to talk about this t-shirt. This is a logo that many of us know, and this is an organization that has inspired both me and the work that we discussed here. It's, of course, NASA. Not only did they go to the moon, but they also did a lot of work with what happens to FRP in service. They formed the foundations of predicting the remaining life of FRP starting in the 1960s. Thanks for listening. Don't hesitate to contact us, give us a call, reach out to us through utcomp.com. We look forward to hearing from you. Have a safe day.